Alrighty, guys, can you hear me again?
Yeah.
Alrighty. Any questions before we begin on stopping times? So we're going to leave this radical derivative theory behind us, and then we'll go into some of the theory, a little bit of the theory that's behind American options. So we have been solving problems with numbers, right? But these American derivatives, the mathematical notion there is optimal stopping problems. And so let me talk a little bit about stopping times. Right. So stopping times, they are often denoted by tau, and it's a random variable. So it's a map from omega, and then here in discrete time, it gets mapped into 0, 1 up to n is a possibility, where n is the number of periods. It also sometimes goes from omega, and then it gets mapped all the way up to and including infinity. This one here is included. This happens in particular in section 5. So it's a random variable that has this very particular property. So this is a random variable that satisfies the tau is a stopping time. If this set tau being n, right? So remember, this here is by definition, it's those omegas such that tau of omega is n. If this set here belongs to Fn for all n, so for all n, either in here or in the bottom one. So we're going to be focusing on the top one. So for all n from 0 to 1 up to capital N. This here is the condition that one can use in discrete time. There is tau is a stopping time. Tau is a stopping time if and only if, and then you can put in a different condition here, if and only if you have tau n, the set where tau is less than n belongs to Fn for all these n's. This one here, this is what people use, and this is good in continuous time. So in discrete time, we have the luxury, we can choose either to use this one or to use that one down there. Either one is fine. The main example that one should have in mind, and the main example that's in the textbook is the following example. So you pick a k, then the passage time, I should say the first passage time. The first passage time this is the first time. So again, open this set here. The first time that a stochastic process, say the stock, gets to be above k. And then of course we also have to say what happens if it never gets to be above k. Well, then And then we define this to be plus infinity if the stock price is less than K and for all in. Right, so on the picture, we'll have our tree. Right, and so we put in a threshold K. And so what would K be in the various? So we have we have 3 coin flips. So in this case, our omega is equal to so what would be heads, 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 tails, heads. So it's heads, so we need a heads, tails, and then heads, heads, tails, tails. How many should we have? 1, 2, 3, we know almost there. So what else do we need? So heads, tails, tails. We also need a tail, and then heads, heads, and tails, heads, tails, and tails, tails, heads, and tails, tails, tails. I think those are all the ones. 1, 2, 3, 4, 5, 6, 7, 8. That works. 2 to the power 3. Right. So the random variable is going to have a number of values. Right. So we could try to work out what is tau at heads, heads, heads. And we have our time points down here. So out here in the end, this is time 3, times 2, time 1, times 0. So let's try to work out maybe not all of them, but let's just do some of them. If I look at tails, heads, 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 what do we get? Well, so now we're on the path. We go up, up, up. When is the first time? When is the first time that we got above K? When is the first time we got above K on the path? Heads, heads, heads.
At time 1.
Yep. So that was the first one. Then we do tau of what would it be? Heads, heads, tails. What would that one be? So now we go up, up, down. When is the first time we got above?
1 as well.
Then we do the next one. Tails. No, tau of head, tails, heads. Heads, tails, heads. When is the first time we got above?
Time 1.
Tails of head, TT. Heads, tails, tails. When was the first time we got above?
First one.
So you can see H here is the determining factor. The first coin flip brings us above. So we're probably going to get more action in the last 4. So let's try the last 4. So we'll have 1, 2, 3, 4, 1, 2, 3. So tails, heads, heads. So we go down, we go up, we go up. When is the first time we got above?
Third time.
And then we'll have tails of heads, tails. So tails, head, tails, tails, head, tails. When is the first time we got above?
Is it infinity for that?
We didn't. So if we're below at all the times, then we put it to be plus infinity, right? And so that was that guy. Then we have these two, tails, tails heads. So we go down. We didn't head it. So it's plus infinity. Tails. This is okay. So how would one see, not in this specific example, but just in general, how would one see that you have a property of this sort for the first passage time? Yeah, how would one see that? You would do something like, so to check that tall, what would the equivalent? So to check that this set belongs to Fn, we can check that the complement is in there, right? Because sigma algebras contain the complement sets, right? So if tau is bigger than n, then if tau is bigger than n, that means we haven't reached it yet. Right? So that means that at all time points before you haven't reached it. So if you haven't reached something at some point, well, then means that the stock price is going to be less than that threshold. And then what we have here, this belongs to Fm, and m is less than n. So we have this conclusion. So this is a stopping time, and that's by far the most important class of stopping times that we have. So I had in mind we should try to look at an exercise. Problem number 25. Let me try to bring that up. I'm trying to bring that up. This one here, number 25. So you see, we have a n-period binomial model. S star is just the maximum, and then we're defining a 3 random variables in 25.1, 25.2, and 25.3, and the question is which ones are stopping times. So the first one, the stock price, you look at the first time that the stock price equals its global max. And then look at the definition of a stopping time. How would that go? Would that work? Would we have a property like the one? If I stop sharing here. Would we have a property like this one? Would we be able to tell whether or not would we be able to tell at time n whether or not the stock price has reached its global max over the period? So the exercise is, if I look at the first time such that Sn is equal to the maximum of S1, S2 up to S capital N, is this a stopping time? Well, no. This involves to check something like tau being less than n. This involves S capital N, and that's not if n measurable. So it involves looking into the future. So here we're looking at the first time that the stock price is equal to its global max. And that involves looking into the future and stopping. That means that this condition here is violated. We can't do it. The second one. The second one was the first time. That was one we just had. The first time that Sn is equal to a constant, or maybe above a constant. This is yes, that was the one we just had. And this third one, this is instead of a min, you put a max. This is the last time that the stock price is bigger than K. So again, you're talking now about the last time that you're above K. Would you be able to tell at time N whether or not the stock price has reached the level K for the last time? No, this also involves the future. So this is a no. So these stopping times, this is the prototype is when you're talking about the first time that something happens. This is something that you can determine by knowing Fn. Did something happen up to time N? Yeah, you can observe that, but you cannot observe stuff that involves the stock price at future times. And so those random times, they're still going to be random times, but you're just not going to be stopping times. And the reason that these stopping times are, so we use them for American options. We're looking at the maximum. So for us, we're looking at, say, the maximum over stopping times of discounted payoffs. So we compute them under the reverse neutral measure of e to the minus, say, r. Typically, we do discrete compounding. So we look at expressions like this one. If we have a put, it's K minus S tau. And then we're taking the max over T, stopping time, tau of omega takes values, say, between 0, 1, 2, up to n. Or you can put in a different intrinsic value here, like the straddle that we talked about in the beginning. This is why it's important for us. So for us, this is important for probability in general. It's important because if mn say if mn is a martingale, then the so this was for us for probability. If mn is a martingale, well, then the stop process, m n min tau, right? So I'm going to define what that is. This here is equal to mn when n is less than or equal to tau, and m tau when n is bigger than tau. Right, so the stop process, if I'm looking at a path of the stock price, so our stock price goes like this. Say this is our stock price. Then what we do is, for example, we stop the process at some time. Say we stop it here. So then the red one would be the stop process, and it just stays flat here forever. So this would be my mn, and the red one would be the stop one. So if m is a martingale, then the stop process is again a martingale. So this happens when tau is a stopping time. this is true for any stopping time. So these stop processes, they play a role in probability, and you also, when you read through the text that we're using, stop processes, they also been used in there quite a bit. So just one pitfall that I've seen is one pitfall I have seen is to work like tau is a constant, and that's just not true. So this is not a good idea. And so let me try to give you the gist of it. If we look at, so this is basically the model that entire section 5 is devoted to studying. You look at a symmetric random walk on the integers. Right, so a symmetric random walk, you have our science. We have our science, and we're going to go up to 1 or down to 1, and you're going to go, it's a symmetric one, so the probabilities are half. So you get the symmetric random walk simply by saying that Mn is equal to the previous one, and then a psi, and it starts out at 0. Right, so this symmetric random walk on the integers, it would look like this. You go up to 1, down to 1, and then here and here, and then you can keep going up, keep going down, and you can jingle. So this is a path of M here. Right, so if I look at tau, this is the first time. This is the first time, if it happens, this is the first time that this symmetric random walk becomes 1. Okay, any ideas about what the probability is for this one being finite? Any guesses on when would if I have imagine that this is a coin flip, right? Every time I flip heads, I go up. Every time I flip tails, I go down. Will I reach the level 1 here? Like that was our first passage time. Will I eventually reach the level 1? I start out at 0. Well, there's a 50% chance that I'll hit 1 after the first coin flip. Okay, so then I'll do it. Okay, so if I go down, then what? Then I need 2 coin flips to go back up to 1. What do you guys think this probability here is? You keep flipping this coin, right? There's no upper limit here. This thing keeps going up to infinity. Will I eventually hit 1?
Is equal to 1, the probability?
Yeah. And the much harder one is, so this one here is much harder. It's much harder to figure out what the expectation is. But for my point here is this thing about treating it as a constant. So given that this is true, this is really true. What is M tau? What is M tau equal to? Well, what is the value of the process M at the first time when it reaches a level 1?
Is it 1?
This is 1, right? So with probability 1, this happens. But you will never have such a property. Like m tau is a constant with probability 1, but mn is not going to be a constant for any n, except for n equal to 0, which is 0 then. So don't treat these taus as constants. You could never get something like this to work for a constant. It's not. So whenever you see a stopping time, this is a random variable, and it satisfies this measurability property, but that's it. Let me show you a little bit about some of the things that one can then do with stopping times. The reason that people treat them, the reason that I've seen students treat them like constants is because they share a lot of the same properties as constants do, but far from all. So let me show you some of the features that like we know. So we know that if I take a martingale, we know that when this thing is a martingale, well, then the expectation of mn is just the initial value. But it's not true. But just because the expectation of mn being m0, we don't have that mn is a martingale. Right, so for example, if you do this symmetric random walk that we had up here, like this symmetric random walk, this was a martingale, right? So we let mn be this symmetric random walk on Z, then that's a martingale. But if I looked at let's call it maybe xn, if I would just take n here times mn, then the expectation of xn, well, this would be the expectation of n mn. That would be n times the expectation of mn. Right, and the expectation of mn, m was a martingale, starts out at 0. So this here is equal to 0. But x is not a martingale. Indeed, if I try to compute the conditional expectation of xn plus 1 given fn, what will I get? Use the formula. This is n plus 1 times mn plus 1 given fn. And then what I'll do is I'll put the n plus 1 outside. Then I'll have the conditional expectation of mn plus 1 given fn. Right, and then I'll use this symmetric random walk we have up here. That is a martingale. So I'll get here n plus 1 times mn. But this is not the same as n mn, which is my xn. So it's not true. If you are a martingale, you have this property, but just because you have that property, it doesn't make it a martingale. You need a lot more. And let me show you how stopping times come into this picture. The stopping times is what rectify this situation here. So let me just show you if so maybe a little lemma. If mn, say from 0 to 1, is a martingale, tau is the stopping time. Well, then tau is the stopping time. Let's just be more careful about exactly what kind of stopping time it is. It's a stopping time that goes from tau takes only values up to n here. then that property that we had with the constant expectation that this is equal to its initial value, this carries over. That holds for stopping times too. And to see it is not too hard. One can, and the way that one typically operates and proves is this proof here is quite indicative of how we would do proofs in general for this stuff. You will take E of m tau. The way we do it is we split it according to the values that tau takes. So I'll write this here as an expectation and then a sum from n equals 0 to capital N, because that's where the possible values are. And then I'll look at the indicator for when tau takes specific values. So tau equal to n, right? And then m tau on that set is going to be mn. And then I can use the iterated expectations from before. Right, I know what mn is. This is a martingale, so I can write this here as an expectation of m, say capital N, given f little n. And so now what I can do is, well, I can put the sum outside. I can put the sum outside. I can put the sum outside, and then I'll have an expectation. And then I have this set here. We notice that this one here, this is by the stopping time property. This set here, this belongs to Fn. But this indicator is Fn measurable, so he can go inside. So this guy can go inside, and so I'll have the conditional expectation of the indicator of tau equal to m, and then m capital N. Right. Tau being a stopping time means that the set where tau is equal to n, this is a set in Fn. Okay, so this is measurable. We can jump inside, and now we have conditional expectation, like iterated conditional expectations. Which one wins? The smaller one always wins. The smaller one is the unconditional one. So we left here with the expectation. We left here with the expectation of 1 tau equal to m, tau equal to n, mn. And of course, this is capital N, this is little n. I can bring the sum back inside, and I'll just get m capital N. And then, given that m was a martingale, this is just the initial point. So again, we use iterated expectations. It allowed me to convert that n here into a capital N, and that helps a lot when I sum over little n's, right? Because then there's no little n dependence. Here, I'll just, when I sum up these disjoint sets, I'll get the entire omega. So I'll get the indicator for omega here. So that's just the expectation. And then here we have the martingale property. This is implied by the martingale property. And what that shows is that when I look at these random variables that are stopping times, I can take a martingale, I can stop it there, and I have the same property as I would have for tau being a constant. So there's a converse to this one. The converse is that if you have such a property here for all stopping times, well, then you actually have the martingale property. So the converse is, so the converse is that, so the converse holds too. If m tau is the expectation of m tau is equal to m0 for any tau stopping time, tau of omega are values up to n. If this is true, well, then mn is a martingale. And that was the missing piece. So this highlights again the difference between stopping times and constants. Right? The example we had here, shows that if you only test this out, at times n, you won't get. But if you test it at stopping times, if the property holds not just at constant times, but at these random times that are called stopping times, well, then you get the martingale property. So this is a much, much stronger condition to satisfy for a process relative to the one that just shows that you have constant expectation at all fixed times. So again, it highlights that these are really not to be thought of as just constants. It's more general. So this was a bit about some of the theory that is underlying this American derivative pricing. The big result that people use, the big result that we also going to that everybody is using when you deal with stopping times is this result by dupe that's called optional sampling. So let me just talk a little bit about optional sampling. So optional sampling. This is dupes. So optional sampling takes a few different forms. If you have a martingale, so you take Mn, martingale, then one form it takes is the stop process. This is again a martingale. So that's one form it takes. Let me show you where you can read more about this. So we're in the first chapter, stochastic calculus for finance. So if you look up dupes, what's called optional sampling. So it's down here at the very bottom, down here at page 99, 100. So this is what he means here. A martingale stopped at a stopping time is again a martingale. That's the one we had here. And then Steve has written a few different ones. He also has one here that says that it relates. So here he's working with a sub-martingale. We can also just do a martingale. He has n min tau, and then he has n here. Let me write that version down too. So you also have that if say sigma is less than tau, tau is less than, say, n, sigma and tau are stopping times. Well, then the expectation of m sigma given, maybe I shouldn't do it that general. Let me just delete the sigma, just stick to tau. So you do m tau. This is the same thing as m0. M0. He wants to have, so that was the one we had up there. If tau is less than n, then the stopping times, and you get that. Steve also wants to have a property that says that if you link them, that it doesn't have to be 0 over here. You could also write this sigma less than tau, and then you could write this here as m sigma. Right, and the case that Steve is interested in is he says let's take sigma to be tau min n. Then Then what would he get? He would get E of M tau min n. You would get that this would be equal to M0. And of course, this is also equal to E of Mn. Because this stopping time here, this is tau min n, this is going to be less than tau. So there are these variations here. There are these variations. So you take a martingale, you could also take a sub. You take a sub martingale. If you take a sub martingale, then this is again a sub martingale. If you take a sub martingale, then sub martingales, you have increasing expectations. So you would then have that this one here would be bigger than or equal to M0. And then you could link them because if you have a sub martingale, you have that the expectation of the biggest one. Sub martingales, you have a tendency to increase. So this would be bigger than E of M sigma. This is the sub martingale case. So you get these inequalities. And all this is called optional sampling. If you have a martingale and you stop the martingale at stopping times, you preserve the martingale property. If you evaluate the martingale at random times, you can relate the expectations on those random times to expectations at different random times if you know that those random times are ordered, like one is less than the other. The application that I want to give here in the last few minutes is the American call. So let's give an application of this optional sampling material. If you look at the American call from your homework, so you have an intrinsic value, your function g of Sn. This is given to be, the call is like Sn minus k. In your homework, you would have realized you should get that you don't exercise this American call before the end of the time horizon. And the section here that spells all this out is the last chapter over in section 5. This is chapter 4.5, American call options. So it's those few pages here I'm going to take you through now. So here we have the American call intrinsic value. And the thing that we're going to be doing is proving that we're going to prove that when I look at the optimal stopping problem, so I take the max over tau of E tilde of 1 over 1 plus R to the tau times Sn is tau minus k. What we want to prove is that this thing here is equal to just the call for the European, so the European call. So this is 1 over 1 plus R to the power n here, and then it's Sn minus k positive power. This is what is being proven in section 4.5. So let me try to take you through the steps in here. So this is a little lemma here. And the proof goes by showing this claim that if I looked at Sn minus k positive part divided by 1 plus R to the nth, this is a sub martingale, and that's the claim. And the sub martingale, those are those processes that in expectation grows over time. So you can see why you want to hold off for as long as possible. This grows in expectation. over time. Right, so when it's growing in expectation over time, you want to hold off for as long as possible. This result here, this is going to require that the interest rate is positive. So I'm going to put that in there. And let's try to see why this is a submartingale. Well, let's try it out. To prove that something is a submartingale, right? There's no stopping time here. We will just compute the conditional expectation of this process evaluated at time n+1. So that's the thing we're trying to compute. So how would one go about doing that? Well, we could move the stuff here outside. Or we could move it inside. Let's just put it outside. 1 over 1 plus r n+1. So I have a plus here. When I'm looking, so what I'm looking at, the call payoff. The call payoff, it looks like this. And so you have convexity here, because if I take any 2 points and I combine them with a straight line, that straight line is above the hockey stick, right? So we got convexity here. There's convexity in this hockey stick. Okay, so that was one thing. So if I have convexity and I have a convex function on the inside, what I can do is I can move the convex function outside. If I move the convex function outside, do you guys remember what happens? Take the convex function to the outside. What happens? Which one is biggest, this one or that one?
The one on the left.
The one on the left is biggest. And who says that? This was Jensen's inequality, right? So now what do I have? I have the discounted stock price, and then I have a K. What should I do? I could move this expression in there. So I'll get E tilde, and then it'll be the discounted stock price is n+1 divided by 1 plus r to the n+1 minus, and then I'll have K 1 plus r n+1. Then I have given event, and then my plus is up there. And now what I have, this is a constant, right? So when I condition, that doesn't matter. And I have Sn+1 divided by the bank account. That's a martingale under the tilde measure. I'm going to get that this is Sn divided by 1 plus r to the power n. And then I have my K over here. 1 plus r, and then I have my n+1. And this is all positive part. Now what happens, I'm almost there, right? I'm almost there. I'm almost there at the 1 plus r can go outside again if you so desire. But the only little problem here is that I would like that to be an n here instead of an n+1. But so I would like to have that this is bigger than or equal to what would it be? Sn divided by 1 plus r to the n. And then instead of having n+1 here, I just want to put n. And then positive part. Because this would then give me, that would give me the expression that I was hunting, right? This would give me Sn minus k divided by 1 plus r to the n. Right, so this one here, we have to have a little bit of thought. So what is the difference? Well, I'm comparing K, and then I'm comparing K divided by 1 plus R. Which one is biggest, K or K divided by 1 plus R? And this is where we're going to use this assumption here. I think we can allow for a zero interest rate if you want. Which one is biggest? Well, here I'm dividing by something that is bigger than or equal to 1. So I'm going to have this property. So if I throw that away, I subtract away less, I'm going to get something. So I have K is bigger than K is bigger than K divided by 1 plus R. I'll see if I can make it look like what I have here. So then if I then look at X minus K, then this is going to be less than X minus, if I put a minus sign, then this is going to be smaller than what's on the right hand side. So this is minus K over 1 plus R. And so then I'll take positive part. Minus K divided by 1 plus R. And this is what I have over here. Yeah, this part here is bigger than or equal to this one down here. So that's the end of the argument. I have a sub-martingale. So I have a sub-martingale. I know that these expectations then increase in time. I want to hold off for as long as possible. So the American call, when the interest rate is non-negative, you don't exercise them. And so we are out of time, but let me just as last time show you variations on this problem here. There are lots of them. Let me just show you if you want to try a little bit on your own. Let me see if I can find this. The exercises that are related here would be, I think it was 13. Yeah, so here there is a 13. So we have an American derivative. So here's your intrinsic value. So it's not the same as what we looked at, but you can recognize here the exponential function, right? And the exponential function is also convex. So again, you're going to get this sub-martingale property. And what that means is that you won't exercise it early. So this was one example of that. There's another block of problems. Let me just, it was 26, this one here. So again, you have an intrinsic value, and you're interested in when can you say something about early exercise premium, what happens if it's a martingale, super martingale, and sub martingale. Like the sub martingale, this is that's the one we've been working on. There should be one more. Yeah, there's this problem 22. It's again, you have an American, and you want to see when is it optimal to exercise. And now here you have a square function. But again, the square function has convexity in it. And as soon as you have this convexity structure, you're going to get a sub-martingale. So it falls into this category up here. And when you have a sub-martingale, you don't exercise it. You can see with a martingale and a super martingale, this is something that decreases in value, right? So then if it decreases in value, you want to get out as soon as possible, right? So you exercise immediately. And of course, for a martingale, it doesn't matter. So there are a few problems here for you guys to work on. So 28, this problem 27 is what we did in the first part of today's lecture. 26 is, so 28, 26, and then 13, and then 13. Are there questions? Any questions before? This was all I had on the menu for today. If that's not the case, then next time we're going to start on fixed income. Fixed income is the last chapter in Shreve 1. So this is section 6. And we're going to be spending a couple of lectures going through that section. Are there any questions before we call quits?
Thank you, Professor.
You're welcome. So there are office hours later this week, and everybody's of course welcome to bring their questions. If not, then I'll see you next Tuesday.